Alrighty, guys. Still in section 3.1, I want to discuss essentially what an exponential function is, clear up any discrepancies between exponential functions and power functions, because they can look similar, and then discuss the derivative of the exponential function. Okay, so first of all, a power function is things like polynomials that we've been looking at previously. So let's say I've got something like this, f of x is x squared, right, or x cubed, something like that. So x raised to a power. Notice this is the function of x. X is the base here, right? The exponent's not changing. The exponent is fixed here. We've got a fixed power. We call this power function. The base is what's changing. All right. An exponential function, you can have different bases, but the base here is going to be a constant, and then the exponent is going to be our variable. So in other words, if I've got the function g of x is, let's say, e raised to the x, right? So you study a lot of these in pre-calculus. That's what's called an exponential function, okay? They look similar, but they're different. The variable is the exponent. Okay, so a different type of function. So this is not considered a power function. It's not a polynomial, right? If you've got things like this built into your function, then you're not dealing with polynomials. So it's a separate type of function. And the thing that throws students off sometimes, though, is they try to use the power rule for the derivative here, and we're not allowed to do that because it's not a power function. Okay. Remember, the power rule says here, if I've got f prime, let me change this to x cubed just for this example. The power rule says bring the power or the exponent down as a coefficient when you take the derivative, and then replace the original exponent with a decreased by 1 exponent, right? So we start with x cubed, we take the derivative using our power rule, and we end up with 3x squared. What folks want or tempted to do here, all right, and if you're keeping notes at home, I'm going to write equals here to show what students do, but then I'm going to fix it with a not equal because these are not correct. But what some folks are tempted to do is say, let's do the same thing here. Let's bring the power down, x times e, and then decrease that x minus 1. All right? That is not the derivative of e to the x. Okay? So if you find yourself doing that, that does not work. If you had we're going to be dealing with e for the most part, but if you've got a different base, same idea. If I have 2 to the x, that's an exponential function. You do not do that. You can't use the power rule for that. All right, so if you find yourself doing something like this, writing an x minus 1 as a new exponent, if x was your variable, go back to this video, do something, try to make a note that says that's not correct, right? Okay. So what is the derivative of e to the x? All right, so there's a short answer and then there's a long answer. The short answer is I can just tell you what it is. It's one of the nicest derivatives you're going to see ever. If you already know what it is, you're like, yeah, I know that one. Then I can show sort of how to set it up using the limit definition, kind of show where it comes from. The depth that I'm going to take that explanation is going to rely, I'm going to do it kind of how the book does it. The book sort of defines the number e in a certain way, as a limit. It defines it that way, and sort of miraculously that limit pops up when we're doing the limit definition. So if I even do it the long way, it's going to seem like whoa, that's weird. But I'll try to talk my way through the limit definition, see if it makes sense. Anyway, if I've got this function g of x, then its derivative, if it's e to the x, its derivative is itself, e to the x. Its derivative is itself, e to the x. Really cool. So easy. Don't get too comfortable necessarily, because if I've got e to, let's say, the 5x, something like that, now we're going to have to rely on something called the chain rule, which is coming up in a later section, right? So if I've got a more complicated exponent, it gets a little bit more complicated, but there we go. All right. Remember the downside to the prime notation is I've got to tell you what the original function is, and here I'm calling it g, and then also tell you what the derivative is. Remember, so I can say the same thing using the d notation. The derivative with respect to x of the function e to the x is itself is the function e to the x. All right, there we go. So it's its own derivative. That's cool. What if I've got a constant on there? So what if I want to know, let me keep this notation over here. What if f of x is 3 e to the x? Can I do that? So I mentioned if the exponent up there is more complicated, I've got to rely on a rule that we haven't covered yet. But that's just a constant multiple, right? And so remember, we looked in the previous video, we looked at the constant multiple rule. I, for convenience, combined it with the power rule because sometimes it combines with that nicely. But it works for this function too. So here I've just got a function e to the x. So the derivative of 3 e to the x is 3, the constant, times the derivative of e to the x, which is e to the x, right? And there we go. So, not really a big deal. Okay. Let's set up the limit definition. So, the limit, if I've got the function, let's say, suppose f of x is equal to e to the x. All right, so just to set that up. Then, f prime of x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. All right, so that's the way that will spread out. In other words, my function is e to the x. So f of x plus h says just plug x plus h in as that exponent. So we end up with e to the x plus h. All right. Okay, so let's go through this, clean this up a little bit. This is equal to the limit as h approaches 0. So I haven't taken a limit yet. If I'm adding exponents here, I'm going to break that apart using an exponent rule. That's the same as e to the x times e to the h. All right. So meaning if I did have the same base and I'm multiplying those two things, I end up adding those exponents. As an example, if you had e squared times e cubed, then what you've got altogether, you've got e to the 5th, right? Here's 2 of them being multiplied times another 3 of them being multiplied, e to the 5, right? So that's the same idea. Where did this 5 come from? 2 plus 3. So if I've got the x plus h, I can do that rule in reverse, split that up. All right, so I've got that minus e to the x by itself all over h. Okay. What am I going to do with this? Now, let me factor out an e to the x from the top here. All right, so this is equal to the limit as h approaches 0 of, I'm going to factor out e to the x and then multiply that by, I've got e to the h minus 1 over h. Okay, and these guys are being multiplied. So technically, you could argue I've got that, right? The numerators are being multiplied right there, and that's all over the denominator h. Okay, I could argue h times 1 if I want to show a placeholder. But what I want to do is I want to keep the h with this term right here. And the reason I'm doing that is because of our nice definition from the book of the number e. All right, so I've got that. So I'm just keeping it like that. Remember, our limit property said I can distribute a limit across a multiplication. So this is equal to the limit as h approaches 0 of e to the x, right, which has nothing to do with h. So that's going to be interesting when we take that limit, times the limit as h approaches 0 of this thing right here, e to the h minus 1 all over h. Okay, let's take both of those limits. As h approaches 0, e to the x is some function of x, right, a function of x. As h goes to 0, this thing has nothing to do, it's not changing at all, it's still e to the x, right, because x isn't doing anything. So the limit as h approaches 0 of e to the x is e to the x. As far as h is concerned, this thing is basically a constant. It's not varying with respect to h. Okay, so as h goes to 0, this guy just stays what it is. This limit right here is 1. All right, so we get e to the x times 1, and then so e to the x times 1 is e to the x. All right, so that's how the proof works. The only part of that needs a little bit deeper explanation, I think, is this limit, right? Why is that 1, right? You can't do direct substitution. If you try e to the 0, if you try plugging in h as 0, you get e to the 0 is 1. You get 1 minus 1, so 0 over 0, right? We get that a lot through direct substitution, and that's not that helpful. I don't know if you can visualize, see what I wrote there in the sunlight there, but yeah, not helpful. So how do we know that this limit is equal to 1? All right. There's a couple different ways to show that. So let me erase what we've got. However, the moral of the story is the derivative of e to the x is e to the x, right? So I'm not going to ask you guys to recreate this one, but you can claim you've seen it, and let's talk about this limit. All right. So let me leave that where it's written for a second. There's different ways to define the number e. Okay, the book says that the definition of e, they say e is the number such that, meaning that it holds up to this thing, such that if you take this limit, it equals 1. All right. I don't know if you guys can see that great. But in other words, it just says E. What number is E, right? You might be familiar. E is approximately 2.7 or 2.71. It's approximately that. But what we're saying is, I could, at this point, it looks like I can plug any kind. I could say E is whatever I want. They're saying that E is the particular number such that this limit will become 1. I don't know about you, that's not very satisfying to me. When I read that in the book, I'm like, yeah, but that doesn't. Why is that limit 1, right? So let me talk about ways to explore that. One thing you could do is you probably use the variable x, change it, but consider the function y equals e to the x minus 1 over x, all right? This function is not defined if x equals 0. Same way this, you can't plug h as 0, right? So you can't just evaluate it by direct substitution, but try looking at this in a graphing utility, such as Desmos or something like that. And this is similar, what I'm asking you to do if you look at this through Desmos, is the same thing I asked you to do for, I think we had that one from the homework, right? You had to look at that on Desmos and try to determine what the limit was as x approaches 0, even though you can't plug it in, right? But where's the graph going? Right? You saw based on where the graph was going what that limit was. So do something like that. Graph this function. Look that it will have some kind of hole or something like that, but it should be trending towards the height of 1, right? So it should have that limit of 1. Alrighty. That's still not that satisfying. So another way that you can do that, and the graph kind of does this, is make a table. So if you've got e to the h minus 1 over h, make a table for h values and get closer to 0. All right, so you could do 1/10 for your h. So plug that into a calculator, plug it in as 1/10, calculate that. 1/10 is 0.1. You could do 100th, which is 0.01, 1,000th, and so forth, which is 0.001. And keep plugging in smaller and smaller values. So essentially what we did in the beginning, kind of make a table, let h get smaller and smaller, see that the output is approaching the value of 1. Maybe check it from the other side with some negative inputs. But yeah, that's the best I can recommend doing right now. The number e, if I have some time, maybe I'll post another sort of supplement video just about its history because it's interesting. But as long as you know that the derivative of the function e to the x is e to the x, that's good enough for our calculations and good enough for me for now. Alrighty, guys. So the next video I get up will be from some of the later later sections. But there we go. Got 3.1 pretty thoroughly covered. All right.